Next video is going to be about our electronics equipment. Okay. So we have quite a few pieces of equipment in here on our desk. This is our stereo microscope we can use to solder. Right. You will not need this in the class. It's pretty easy to turn off the light, look through the binoculars, adjust the magnification, and adjust the height. You will use this extensively in VME 310, and if you want to do good solder. Okay. And over here we have our solder station. It has two items. One of them is hot air, and the other one is regular solder tip. Right. It's pretty straightforward too. You need to set temperature and to turn the device on, and there's a switch all the way in the back too. And the equipment actually I would like to talk right now about are these ones up here. So what are those 1, 2, 3, 4 different devices? This one up here is a 2-channel oscilloscope. This one is a programmable power supply. This one is a digital multimeter, and this one up here is a function generator. So I'd like you to be able to operate each one of those devices. And we will start with the function generator. So if you look at our desktop here, programmable, not function generator, programmable power supply, excuse me. Right, we have manuals on the Salter Lab website for these things, and for our lab we also need a 5 to 100 kilo ohm resistor. Anyone's good. Black cables with alligator clips, they're already attached, and we need to write up the results of what we're doing. So I don't need an essay, I just need numbers. Okay? Instructions below do not state exactly which ones you will need to push, okay? But I will show you here. We'll turn on the programmable power supply. They all have a button. It actually takes a while to boot them up, so I will just turn them all on so they're ready when we need them. Oh, interesting, they all have a slightly different behavior. Some of them run right away, other ones will take a while to start, and some of them don't seem to be plugged in. Not to my liking. Let's make sure. Okay, we now have all of them running. And the first assignment is we want power coming out of our programmable power supply, like this plus, minus. This is ground, goes to building ground, and I believe these two can be used for additional sensing of the power. But these are the two we want. And the output we want is, what did I say, 3.5 volts. So when you turn this on, you have a button here, and it goes push it, can't really do much wrong, move it forth and back, and I really want to change this number. So I want this to go to 3. Okay, move it one over, 3.5. Okay. Do I now have 3.5 volts between those two pins? No, because I haven't turned it on yet. Next assignment step here is limit the current to 100 milliampere. So this device can actually also control how much power is being delivered. So we would like to go to this setting. Right now it's set to 1 amp, so we need to push these buttons. I want this not to be larger, I want this to be 0.1 amps. Why do I want to do this? If I short these two, or if you have connected your circuit and you accidentally short something, you will make sure that there is no more than 1/10 of an amp going into your circuit. If this is a large number, you will have a lot of current, it will heat up really fast, so you can actually protect your device from a short, from an accidental short. So now we want the resistor to be connected. Let me go grab a resistor. So I got here a pack of 10 kilo ohm resistors. There's a whole bunch of loose ones in here. I don't want to just use up the the nicely attached ones. Okay. So how you make sure that this is the correct resistor? You can read the value based on the color code. This would be brown, brown, black, right? Or we could actually measure them. For that purpose, I briefly go over to this device. Right, that right now is set to measure voltage. I will briefly set this to measure resistance. I attach it here. There's really not much current coming out of this device, so it cannot really shock me. But on this side here, I'm not touching it. And it says 10 kilo ohms, 9.8, that's 10. Right? I could even touch it on this side too, but then I will have a lower value, because now it also measures the resistance between my fingers, so you don't want this. Okay? Ideally, you would have this on a surface and you touch it this way. Okay? So we have a 10 kilo ohm resistor. We want to attach it here and here. So you can do your high school math or high school physics math. 3.5 volts divided by 10 kilo ohms, 10,000, should give you the amount of current flowing through this device, right? It's supposed to be much less than 0.1 amp. There's nothing flowing right now because the output is not turned on, so I turn this on. Okay. Current flowing this device is so small that you can't measure it. Okay, but it has 3.5 volts. I can wiggle. It really is less than 1 milliamp, so therefore the device cannot see this properly. Right? It's probably 0.3 milliamps. Okay, so the assignment says here, enable the output. We did this. Check on the values that are being displayed. We already saw we couldn't see anything. Do they match your expectations? Now is a good time to explain why we couldn't see anything. Okay. So next thing, we will turn on our digital multimeter. Digital multimeter is this device over here. Okay. Attach the measurement lead so that the black cable is plugged into the common. Right. It says here somewhere, see your common. Okay. This is our black lead, and the red lead to be designated to voltage. So up here it says V, omega, triangle, capacitor. So with these two leads, we can measure voltage, we can measure resistance between those, we can see whether there's a diode attached or what the capacitance value is. Right now the setting here is for omega, that means ohm, that means resistance. So what is the assignment? Measure the potential over the resistor which those leads and report it. Okay, so this is direct current voltage. Okay, there's no alternating current, no changing current. It's supposed to be about 0 volts. There's some noise on the line, so that's what it measures. So what is your expectation if you measure this and this one here? Of course, we programmed 3.5 volts, so we should see 3.5 volts. What do we see? This says 3.4973. It's not, no digit is changing, so that's really precise measurement. It is maybe less than a thousandth of what we programmed in the power supply. Okay, so this is what you would expect. So what's the next section in our assignment? Turn off the programmable power supply and use a digital multimeter to measure the resistance of your resistor. Okay, so we would need to go back here to measuring resistance. It says overload because there is nothing connected, right? If you now would connect those two together, you would really start pushing the fuse inside our instrument. You cannot measure resistance while the device is energized. Okay, so we turn off the power. You should take this off too. You can measure here and over here. And I'm measuring 9.8, and if I move this a little bit forth and back, because there might be some contact resistance, it is still 9.8. That's close enough for a 10 kilo ohm resistor. Okay? So what's the next assignment step here? Measure the resistance to your resistor. Configure the leads of the digital multimeter to measure current. Oh, now we actually want to see not just the voltage, we actually also want to see how much current is going through our resistor. Right? So what we want, it's a circuit like this. So we have power coming in, it would be going through here. Second, show this other camera. Okay, so we connect this back. There will be current flowing out of the positive, going into your resistor, going back, and then flowing all the way back into the system. So this is your electric circuit. We want to measure how much current flows through the system. The only way to measure this is by breaking the current, push this through here and down here. Right? On the top you measure voltage, resistance, conductivity, capacitance. On the bottom one, you measure how much current flows through these wires. So we would now need this guy to go here. Okay. And whatever's coming out of the device, right, the current flows through this cable into here, comes back out through this. Now it's in the air, so we want this to be connected to the output. Okay. So again, I will not attempt not to touch this to the best of my ability. And now we need to put this into conductivity mode. So this is DC, direct current voltage, and up here it says in blue, direct current I, that's for current. So how do we switch this? We push the shift button and this. Now it displays microamps DC. Okay. -1. Right? You haven't turned it on yet, so this is really an offset, a DC offset. It's like 0. Let's turn it on. Okay. So the amount of current flowing through our resistor is 0.35 milliamps or 350 microamps. This is consistent with 3.5 volts divided by 10 kilo ohms, 10,000 is giving you the value in amps. Right? And you can see this is extremely precisely measured. Right? This is less than 1,000 because this digit is not changing, and this is changing very slightly. So this is almost 1/10,000th precision of the scale. Okay. So we turn off the circuit, turn this off, put it back down here. Wait for a second. We completed measuring resistance, measuring voltage, measuring current with the digital multimeter. We completed programming the power supply, turning it on and off. The next thing we will want to do is working with oscilloscope. For that purpose, I will have to move the camera slightly to have a better view in our oscilloscope. Okay? So let's take a look what the assignment here is. Attach the leads to... Well, we already did this, we already measured current. Now connect the measurement lead to the channel 1 and turn on the oscilloscope. So this is our measurement lead on the oscilloscope. Right? Sometimes these leads are not connected. This is one lead. This is the second lead. Right? We only need one, so we can take this off again. These are called BNC connectors. It's like two knobs sticking out. It needs to go in here and turn. Right, so Let me take off one of those leads, put it away, try to explain to you what this is. So this side here is your ground. This would be your minus, or whatever is your reference. And this tip here is measuring the difference between these two pins, displaying them. Okay. So inside this connector, the round shiny part is your signal going in, and outside is your ground. That's usually also the insulation of this wire. So inside is one wire, and then outside is a tube with a wire connected here, and we pick it up on this side. Also here you can see there is a magnification. We can reduce the signal by 10 by moving it over here, or leave it at 1 over here. If you want to measure this directly, you can remove this and attach a cable like this one. Right. Okay, that would not be helpful because it's the same on both sides. Let's check another one, like this one, right? It has the measurement signal, it has the ground, and this could be attached here. It's a measurement. When you use it this way, you have a magnification of 1, right? So we somehow need to make sure that the input is 1 in this case. So what the assignment is to use your leads. So let's attach the lead again to this setup. You turn this until it goes in, and then you turn the outside to attach it properly. Okay. So the next assignment step here is to connect the lead to the calibration terminal of your oscilloscope and to push the default button. So let's try to find this. Okay. This is a reference, 1 kilohertz square wave. So we want to connect this here. Okay. And down here would be ground. We do not need to connect ground because this is already connected to ground. If you would use a function generator, you would need to connect this to the ground of the function generator. Now, where is our default button? Here. This is a poor man's way of setting oscilloscope, because you push it, and voila, magically it tries to figure out. Okay, that was not poor man's, because it really should show your signal. Okay, and it did not automatically set it to the best configuration. Okay, so I did a whole bunch of things here at once. So what did I do? The signal's connected, we have square wave. This knob here adjusts the height of your signal, right? Volts per division, 5 volts per division, 2 volts per division. And you can see with this knob we can move it up and down. Let's move this a little further down and make it large. Right, there is this grid. You can barely see it on the oscilloscope. I make this larger. Now I have 1 volt per division, and now I have. Let's keep it at 1 volt to make it a little simpler, and we can count. There's the ground, one line, second line, third line. So this is about 3 volt signal. Okay. In this case here. Now. The same thing is mirrored over here, but this channel is turned off. This is enabled because it lights up, and this channel is turned off, nothing's connected. And horizontal, there is also a signal 200 microseconds per division. So 1 division goes up and down, it actually pretty much falls onto those 2 lines. So half of our oscillation, right, this will be half a wave, the other half, and then it starts again. So this is 500 microseconds because it's 1 division wide, another division wide, 500 by 5 plus 500 would be 1 millisecond. So that signal is 1 kilohertz because the distance between up and up is two squares, and 1 square is half a millisecond long. Okay. So let's take a look at our assignment here. enable channel 1, we do this, adjust vertical and horizontal settings until the square wave is placed properly on the screen. What does properly mean? Right? This is not properly. This is not properly because it's outside the range. Properly is okay, now what did we do? 50 millivolts still outside the range, right? It's 3 volts. We need to see the signal properly. When this starts moving up and down, I can also set this level. This line here is this point. It will start displaying the square wave at this blue triangle at this level here. It's called the trigger level. So when the signal passes this level, it will start displaying a signal. We want to see a little bit more accurate. Right? Now we can see there is a sharp change, and you can see this weird thing right up here. So if we zoom in more, you can actually see there is a limited bandwidth of being able to display a signal that is a square wave. It's a square wave, but you need very, very high frequencies in this signal to remain here a square. Right? So the less bandwidth you have, the more you will have artifacts of these sharp changes. Okay. Make sure the trigger is set to auto. That we already did this up here. And uses channel 1 as its source. So let's see auto. Set up the trigger. It triggers on the edge. It triggers on channel 1. If it's set it to channel 2, by pushing here, it's really not making any sense because channel 2 is not connected. So it needs for the display, the trigger, to record the signal always at the same place. Will need to be set to the channel where it is coming in. Measure the amplitude of the signal manually using the cursor button. Okay, we have a cursor up here. Okay, so what do we want to measure? We want to measure horizontal or vertical. In this case here, let me see. If I have the cursor, you can move this forth and back, and I believe if I push only, now the other side is moving. I move it up and down, so we want to measure from here all the way up here. Right, and in my measurement here, this is the delta is 3 volts, 3.05. That's as good as I could measure by hand. What else does it say to measure? Measure the amplitude. Now we need to measure the time. Right? If you push one more time, both of them are moving together. And if I guess if we push one more time, then we can start here. This will be the start. We push one more time. Right? This would only be half. We really want one period. That's all the way over here. And if this would be sine wave, right, you would see this right away. So what does this say now? It says the difference is 998 microsecond, that's 1 millisecond, and it's 1 kilohertz. That's what this signal indicates here. We measured manually. Calculate the frequencies, I already showed it to us. Now we can actually do this automatically by engaging measure. So we have here measure, we don't use the cursor anymore. Right? And so what are the measurements that we are seeing? Okay, we have source 1, that's what we want. To type, which measurements do we want to see? Peak to peak. The assignment is V peak and frequencies. So we have peak up here, and we can see where we can set frequency. In a second. Okay, frequency is over there. Oh, we just passed it. We actually want frequency. Alright, and now it shows here peak to peak, period, and frequency. And it does this as soon as we put the measurement button. We selected which measurement we want to be done. Peak to peak is actually 3.1 volt. That's from the minimum to the maximum, not an average. And the period is around 1 millisecond, right? It switches slightly by 1,000. So we completed that assignment too. Right, so we measured peak to peak and the frequency using measurement button. So the last two steps of our assignment are concerned about function generator and the digital multimeter. So it says here, turn on the function generator, program its output to produce 10 kilohertz sine wave with an amplitude of 1 volt and a signal offset of 1 volt. So the average signal needs to be 1 volt, the shape of the signal needs to be sine, and the amplitude, right, peak to peak will be 2 volt and amplitude is 1 volt. So let's see how we're going to do this. So the function generator, it shows a nice picture. Okay, what is the frequency? It says 1.00000 kilohertz. Okay, is this right? Is this 1 gigahertz? No, because it's not comma, it's point. So this is actually 1 kilohertz signal. We said we want 10, right? This is a 10 kilohertz signal. Peak to peak, right? Amplitude is 1 volt. That means it goes up 1 and it goes down another 1 from the center. So peak to peak would have to be 2 volts. So we use this button. So the next, okay, maybe this one. Parameter. Okay, now I'm confused. Oops, we didn't want this because I want to go to amplitude. So it says here amplitude. Okay, now amplitude is engaged. So this would be a 2 volt amplitude, 4 volt peak to peak. We want a 2 volt peak to peak. And it says the offset needs to be 1 volt. Right now it's 0. So right, we're going to shift this up by 1 volt. Phase. Now it's 0. That means we could shift it along the axis. Doesn't really matter. The other setting here I would have to read the manual. But let's see. We can have here an output. We can engage it. So now we're supposed to have between those two pins a 10 kilohertz 2 volt peak to peak signal. So let's see whether this is correct. For that purpose, I will attach a oscilloscope. So give me a second. So I will connect the signal here, right? For example here, and we can select the ground on these two items here. I'm making sure that this is 1, magnification 1. And I will try to move the camera over gently. Okay, that will not work. Give me 1 second. Sorry, the light is not particularly good because the sun is setting, but now on this display you can actually see that it's a sine wave. You probably want to zoom in a little, okay? Maybe figure out where the ground is. Right. This arrow here on this corner shows ground, the oscilloscope, so it starts at 0, goes all the way up, so the average signal is above ground, and so we can try now to engage some of the measurements. Measurement peak to peak says 2 volts. That means I have an amplitude of 1 volt. The frequency says it's 10 kilohertz. That's what I asked you to do. Now the last thing we would need to measure is the average of the signal because we have an offset of 1 volt. So let's see which one that would be. The mean, right? Let's go back to gauge the mean. Okay, the mean value is 981 millivolts. Pretty close to 1 volt, so we'll see that there's a slight discrepancy between the two devices. Okay, sorry you can't really see this well. Let me see if I can block. Light, if I put the measurement up. So for the remainder of the assignment, we'll actually want to use the digital multimeter and not oscilloscope. So I will unhook it here. Be careful not to bend this hook. Let's disconnect here. And let's connect the digital multimeter. Please make sure that this pin, this connector, is not at the bottom. We don't want to measure current. We don't want to blow the fuse of this device here. So we put this on the top. For measuring voltage, we will switch the display here to display voltage, DC. Right. And what do we see? We see 1 volt DC. So the DC component of our signal is the average. This device measures something called root mean square. We square the signal, comes positive, we take the average and then take the square root. That's the same thing as integrating the signal and looking at the average, regardless of the frequency, right? We can go up here to frequency, we can increase frequency, it is not supposed to change, right? Lower frequency. The average signal is determined by this DC offset reset. So let's see what happens here if we move to AC voltage. What would you expect? I would want to see the amplitude, how much this changes. Okay, it's 0.7 volt AC. Why is this 0.7 volts? Let's try, because assignment also says we should switch to a different type of waveform. Right? This was sine wave, let's move it to square wave. Oh. Now in a square wave we have exactly 1 volt. Right? Up and down, 1 volt. However, if we go back to this waveform, although it's the same amplitude, this is smaller. So this instrument here measures a time average, root mean square. It measures the integral of this function. So if it's a square wave, the integral is max, max, min, min. It's 1 and 1 on this side. 1 up here, 1 here. Here the average of this waveform is 0.7, that's the integral of the sine. So this is what you're going to see here. Right? This times the current is giving you the average power that your device consumes or produces with the sine wave. If you switch to a square wave, right, you will consume more power with the square wave because the voltage stays up high and low longer. In the sine wave, in average, it's not. The max is 1, but the average is 0.7. So to turn off equipment, you push the button. It doesn't turn off right away, so you need to push it for a little while, and then it goes away. It turns off. These cables, we don't let them lay on the desk. You put them back up here. Same thing over here. Right? And again, you turn it off. Here we just push the button. I think our equipment is on its place and put away. Right? We looked at stereoscope, soldering, function generator, digital multimeter, power supply, programmable power supply, and oscilloscope. I think that's it for today. Eska, you want to say goodbye? Where are you? Eska? Yeah, say goodbye. Bye-bye.